In this video, we're going to be talking about our overall strategy for testing series. So let's remind ourselves what the different convergence and divergence tests that we have so far are. We actually have a total of 9 tests. So up to exam 2, we had our p-series test, the geometric series test, the divergence test, and the integral test. Okay, so since then we've also learned 2 different comparison tests. We have our plane comparison test that uses inequalities, okay, in terms of comparing our 2 different series. We have our limit comparison test. We've also learned the alternating series test. And then most recently we have our ratio and root tests. Okay, so that's a total of 9 different convergence tests that we have to choose from. So we want to think about our strategy in terms of when is which one of these tests going to be most appropriate. We've talked a little bit about strategy throughout each of these different sections, but now that we have all of these different tests, we want to think about what are the clues in a series that tell us which will be the most appropriate test to use. So our goal, sort of like when we were determining the appropriate integration technique to use back when we were talking about different integration techniques, is to think about the form of the series that we have, because there's certain forms in which a particular type of test will be most useful. Couple of other general sort of tips. Sometimes it's helpful to write out the first few terms to help you see what the form is. That's particularly helpful in seeing if your series is geometric and seeing if it's alternating. Okay, are you actually seeing a pattern of plus minus plus minus? Are you seeing a pattern where you're getting to the previous term by multiplying by the same number each time? Okay, so let's go through and think about what sort of steps we might use for determining what test we want. So the first thing that you want to ask yourself often when you're looking at a series is it a straight up p-series or is it just a geometric series? So those are the 2 sort of easiest things to identify right away. Is it the form the sum of 1 over n to some number, or is it some kind of sum of numbers raised to powers of n, where if you wrote out the first several terms here, you'd realize to get to the next term you are always multiplying by r. Okay, so if it's a p-series, you want to use the p-series test. If it's a geometric series, you want to use the geometric series test. Okay, so what else? If it's not strictly a p-series or a geometric series, but it's similar to one of those types of series, then we can try a comparison test. So when you're trying to decide between using the limit comparison test or the direct comparison test, it's usually a good idea to try the limit comparison test first. Usually that's going to be a little bit easier. There will be some cases where the limit comparison test won't work for you because you'll end up maybe with the limit not existing or something like that, in which case then you'd have to go over and use the direct comparison test. But most of the time it's a good strategy, once you've decided to use a comparison test, to try the limit comparison test first. So here are a few additional notes on types of series where we want to try a comparison test. If the series is made up of powers of n, like this sum here from n equals 1 to infinity of n squared minus 5n over n cubed plus n plus 1, or here we have a sum of a square root of n plus 2 over 2n squared plus n plus 1. These kinds of things made up of powers of n, we're going to want to compare to a p-series that we determine by looking at the sum of whatever the highest power of n in the numerator is divided by the highest power of n in the denominator. So for this first series here, this would be compared to a sum of n squared over n cubed, or 1 over n. And this second one here would be compared to a sum of like root n over n squared, okay, which would be 1 over n to the 3/2. Okay. We do need to have positive terms anytime we're going to use a comparison test. But if our series does have some negative terms as well, think about looking at the sum of the absolute value of the terms, because then that will be something that does have all positive terms. Maybe you can apply a comparison test to that series. If you can show that the sum of the absolute value converges, then your original sum converges. Okay, because if the sum of the absolute value converges, the series converges absolutely, which means the original series also converges. So you just want to keep that option in mind. So next kind of easy thing to check is, can you see that the limit of the terms are not going to 0? If your terms are not going to 0, then you can go ahead and apply the divergence test. Most of the time your terms are going to go to 0 and the divergence test won't be helpful. But if you can see that the terms are going to some number other than 0, divergence test is good to use then. If your terms alternate, positive, negative, we're going to try the alternating series test. So what are our other big clues of types of forms? Well, if you see a factorial, or you see products of exponentials and other kinds of things, products of an exponential and a power of n, products of exponentials and factorials, we're going to want to use the ratio test. Okay. Now, if we have some kind of series here like before that's made up of sums of powers of n, okay, just powers of n, then the ratio test won't be helpful. We'll get 1 for the limit of the ratio there, and it'll be inconclusive. But if I have some kind of powers of n times an exponential, something like this, okay, I can use my ratio test. Okay, so powers of n by itself, ratio test won't be helpful, but if I have a product of a power of n and an exponential, a product of a power of n and a factorial, ratio test will be helpful in that case. If the terms of my series have some kind of power of n, everything's being raised to some sort of power of n, that's when we want to try the root test. Okay. And remember, root test is inconclusive when ratio test is inconclusive. So notice that our last kind of test that we would try would be the integral test. Okay, integral test is long and complicated. Sometimes we need to use it, but we're always going to try another test first. Remember that some signs that the integral test would be helpful is if you take your associated function here, f of x, where f of n would equal a sub n, the terms of your series, if integrating that function wouldn't be too bad, you kind of look at it and see you could use u substitution or some nice antiderivative rule that you know. If you see that it's not too bad to evaluate, then you might think about trying the integral test, as long as you have the conditions of that test being satisfied. So that gives you a general strategy to follow when choosing what test to use.